Almost every object you see around you, the chair you are now sitting on, the cup you may be drinking from, not the cookie you last ate, but definitely the box it came from and the machines that were used to make that cookie, have all been once designed by a mechanical engineer using a parametric CAD tool. These models are everywhere and are widely available in online repositories. They are parametric from construction and capture the engineer's design intent, including manufacturing considerations. Working with these parametric data, however, is challenging because CAD requires longer generation times and resulting meshes have different combinatorics. In our work, we address these challenges using precomputation. We sample the parametric domain in an adaptive grid, and because each sample is a mesh with different combinatorics, we propose novel interpolation schemes that exploit the underlying CAD representations for finding correspondences inside each element and define smooth interpolations in this domain that guarantee local influences for each sample. Our method can be used to explore the space of geometry variations in real time. Further, we can display physical properties for this bike frame, such as the total mass and the drag from a given wind direction, which can be computed from the mesh in interactive rates. Other properties, such as stress distribution, which depend on time-consuming simulations, can be pre-computed at each sample and interpolated with the geometry. For this chair example, the surface area is computed as a function of the interpolated geometry, which is updated in real time and displayed along with a pre-computed stress and deformation that results from an external force acting on the seat surface. In this wrench example, the varying mass is displayed along with the moments of inertia shown in the red and green axes. These properties are evaluated in real time from the interpolated geometry, and the stress is interpolated from pre-computed FEM simulation. On the swing example, which is coated with expensive material, the surface area is evaluated in real time and displayed along with a pre-computed stress distribution. In this example, we vary not only the shape, but also the direction of the force, which ranges as the child swings. In this camera mount, the engineer aimed at minimizing both the weight and the deformation on the connecting faces while making the stress distribution as even as possible. The holes were designed as circular patches to be fabricated with drilling, which is far less expensive than milling, and illustrates how our method can be applied for optimization with fabrication constraints. In this airplane model, we displayed the drag forces from a frontal wind and the moments of inertia in the green and red axis, which are computed directly from the interpolated geometries, and display the air pressure distribution on the model, which is a result of pre-computed fluid simulation. And this example shows a thermal expansion that is coupled with a stress from the brake hub. The pre-computed simulations include the heat distribution, deformation, and stress. The heat source is uniform on the inner wall, while the forces from the brake hub are directional. Notice that as the thickness increases, the deformation on the rim becomes more uniform, since the impact of the heat outweighs the directional forces. We also show how our smooth interpolation can be used to couple our pre-computed data with optimization algorithms. In this example, the arbor press is optimized for two different use cases. The height and width are constrained by the application, and our algorithm optimizes the other three parameters to minimize the stress on the model. These examples show how our method can be used to allow designers to interactively visualize or automatically optimize CAD shapes for different objectives. And because it allows real-time geometry generation and continuous derivatives, it paves the way to applying parametric CAD data to many works in the growing field of fabrication-oriented design.